Hello everyone and welcome back to another video of NL Maths. Today we're talking about one of the highlights of derivatives, solving nth order derivatives. So that's in the form of x to the n, but this isn't power, this is to the nth derivative, and we need to multiply by a constant, plus a n minus 1, x n minus 1, plus dot dot dot, a 2x dot dot. So this n minus 1 is of course the n minus 1 derivative. X dot dot is the second derivative according to time. Plus a1x dot plus a0x equals 0. Okay, and to make our lives easier, we're going to do something. We're going to divide the whole equation by a sub n. Because we can then get this to have no coefficient. And these are still constants, so really we can still use the same notation, it's still the same thing. But before we do any more of that, I would like for you guys to understand one simple one first. The solution to a1x dot. Okay, so we've got this, x dot equals lambda x. That is our equation that we're going to solve first. And because, why are we solving this? Because the answer to this is very similar to one that has multiple nth derivatives. So x dot is of course equal dx by dt, the first derivative according to time, and that equals to lambda x. So whenever someone asks a calculus student how they would solve this, they say separation of variables, the easiest method. So then we times this by dt, and we divide by x, so we get dx over x equals lambda dt. Then we can integrate this, and we get ln of x is equal to lambda t plus c. Okay, good. Now we can raise both to the power of e. So for the first one, it gets rid of the e to the ln. Second one is a different case. So then this would be x, and I'm going to change something. This would be x of t, because it's a function of time. It was a function of time from the very beginning, because it depends on time. And this is going to be e to lambda t, multiplied by e to the c, because of our exponent rules. If you have two of the same base, you can have them multiply together to give the same result. And whenever we have a differential equation, I've mentioned in my previous video, we need initial conditions. We need x of 0 or maybe x of 5. We need initial conditions somehow. Because let's say we have, perhaps another example to give you why we need initial conditions. Let's say we have a pendulum. Let's say it goes there at a certain speed and the speed is equal. But maybe after 1 second, with this speed, it's going to reach the middle. However, if you are at the middle and you're still going at that speed, you're going to end up here. So different initial conditions will lead to different answers. So maybe if your initial condition was this, then your answer is this. But if your initial condition was this, then your answer is this. So it's very different. Okay. I do not know where my rubber went, so I'm going to be using my finger for now. Okay, so now let's say we have initial conditions x of 0. Then we have x of 0 equals e, but t is going to go to 0. So that's e to the lambda 0, which is 0, and e to the 0 is 1. So that I can delete that, and we have e to the c. So the initial conditions will be this constant e to the c. And that depends on, of course, this equation. So then we have the final answer, x of t is equal to e to the lambda t times x of 0. So I'm going to write this out. So for this equation, x of t equals e to lambda t times x naught. So that's the answer to this particular differential equation with the first derivative. And I found my rubber. Okay, but what if we want to solve these nth order ones, these higher derivatives? Then the method to do it is that we're going to put it in a matrix system of differential equations. They're all coupled, but what you will see is they're all first order derivatives, and that's going to be very easy for us to compute, and I'll show you why later. Okay, I'm going to use the blue pen for this. Okay, so we have d by dt of, and as you can see, we have lots of x's here. We've got this x, we've got this x, we've got this x, we've got this x. So actually, I'm sorry, we're going to introduce some new variables first. And this is going to help us with making one ODE, so one ordinary differential equation, which is to the first order. So we're going to say x1 equals x. So x1 equals x. This is x1. Then x2 equals x dot. So as you can see, if we work with these x1s and x2s, then we're only going to get a single ordinary differential first order one, because they're already including the information that's a dot. Then x3 equals x dot dot, and etc, etc. So then this goes on until x of n equals xn minus 1. So x of n is the n minus 1 derivative. So what you see here is that we don't have this x of n yet. We don't have that at the nth derivative yet. We only have the n minus 1 derivative. So we want to introduce something else as well. We want to introduce the dots, like the derivatives. So the dot of x1 is going to be x dot, which, as you can see, x dot is equal to x2. Good. X2 dot, which is x dot dotted, it would be x double dot, which is x3. And x3 dot equals x4. As you can see, there's a pattern. Then xn dot is going to equal to xn, but this is also equal to, and this is important, so I'm going to write it down here. If you take x of n and you take all of these other terms onto the other side of the equation, that's going to be equal to xn, because we need to include all of this information. So xn dot equals negative a0 x0 x1 minus a2 x2, sorry, a1 x2, a1, and x dot is x2, and minus a2 x3 minus dot 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 an minus 1 xn. Okay, good. So we have all, because this is xn. Good, we have all of this information. Now we can put this into matrix. So we're going to use this space filler. So we are taking the derivative of a matrix, which is going to be our x1, x2, x3, x4. And this can include all the information about our original system here, and you will see why later. So x1, x2, x3. Actually, I'm going to increase the space so it's easier. Xn minus 1 and xn. Good. So now, as you can see, since x2 is like x dot, we can take the derivative of x, so we can get x double dot, and that we'll see how it matches with our system. And this is going to be equal to a big matrix multiplied by x1, x2, x3, x4 continuing. So let me just write that down. x1, x2, x3, dot dot dot, xn minus 1, xn. So it's like how much of x1 is in x1 dot, etc, etc. So so what we do, derivative of x1 dot, so is x1 dot, which is x2, as you can see. x1 dot is x2. So we can write this as 0, 1, 0, dot dot dot, 0, 0. And what this means is that if we flip this matrix like so, then it's 0 of x1 plus 1 of x2. So I'll just write this out, and I'm going to erase this really quickly. So this means that 0 times x1 plus 1 times x2 plus 0 times x3 dot dot dot. So this is what contains the information. So x1 dot is equal to 0 x1 plus 1 x2, so it's equal to x2. So good. Now I'll just fill in the rest of the matrix. You can do this yourself for an example problem, and perhaps that is going to help you as well. So of course x2 dot is going to be x3. Then we have 0, 0, 0 because it's not included. It goes down a diagonal. Then I'm not going to write the rest. And then it's going to be xn minus 1 dot, which is going to be xn. So this is going to be 0, 0, 0, 0, 1 because xn is the last one. Then the final one is going to be quite different. So I'll be using green for this final line. And because xn dot is xn, and we saw that xn dot is equal to negative a0 x1, negative a1 x2. So we can write that. Negative a0. As we can see, it's a linear combination. So x1 times negative a0. Then this one is negative a1, negative a2, dot, dot, dot. And then we get negative a minus 2, n minus 2, and negative a n minus 1. Because xn times negative a n minus 1 equals x dot. So, good. We've got a matrix system of differential equation, and it's all to the first order. It's the first order differential equation, which is what makes it so easy to deal with, and is what we love about doing high order and order derivatives. This is what we do for most of them. They're all coupled because they all depend on each other. And this matrix, however, can be hard to use. So we're going to go on to the main topic of today's lecture, which is diagonalization. Sorry, let me just check my notes. And diagonalization is really important because diagonalization matrices are very easy to deal with. So I'm going to flip the whiteboard over and we're going to talk about diagonalized matrices. Good, good, good. Okay. So let's say we have a matrix A, which is diagonal. And I use this underscore to denote that it is a matrix, of course. And these, if you have A, which is diagonal, it's going to lead to decoupled dynamics. Decoupled dynamics, which means they don't depend on each other, and you will see why this is the case later. So remember our first order differential equation that we solved at the very, very beginning of this video. I like to think of this maybe with an intuitive sense, maybe the population of giraffes. So the change in giraffes over time is just equal to a specific constant, and that's how they reproduce. And then if we have x dot equals ax, which means there's multiple different differentials, then that'd be the population of whole zoo, so including the bunnies, the wolves, all of them, but they don't depend on each other. Depend on each other. And we will see why this is the case now. So let's just say we do the same as we did just now with the d by dt equals something. But I want to show you something before. Actually, I forgot to mention this. With this equation, it is very important to note that this is a matrix. And let's say this is x. This is going to be A. And this is going to be x again. This, as you can see, I'm going to write it here. X dot equals ax. And this is what makes this so amazing. This is the relationship between linear algebra and differential equations. This is what makes it so beautiful. Such a simple equation. And we're going to see this with the population of animals in the decoupled dynamics as well. As you can see, x dot equals ax. The matrix. Okay, so, good. We have d by dt. And let's say, perhaps we do the same method. X1 would be population of giraffes. X2, population of bunnies. Until x of n. And this, of course, is our X matrix. Then A, since it is diagonal, and this is what's so good about diagonal matrices, we will have lambda 1, lambda 2, ... lambda n. And the rest of the matrix is going to be just filled with zeros. And finally, we have that multiplied by x again. So we have this multiplied by x1, x2, ... xn. And this is going to be equal to x. Sorry, wrong pen. And this is, of course, our matrix A. So if this was the case, actually, so how would we find x dot of the giraffes? Well, that's easy. We flip this over, and that'd be x1. So x1 dot equals lambda 1 times x1, and then plus 0 times x2 plus 0 times x3, etc. So these terms all go to 0. Then x2 dot is going to equal to, and we flip this, so it only matches with the x2 term, so it's 0 times x1 plus lambda 2 times x2. And you will see why this is so easy, because we've solved this at the very beginning of the lecture, this first order differential equation, and we all know how to solve this. So then we can say that the answer to this whole system of equation is x of t equals 2 e to the lambda, so e to the at times x0, because we're just doing the whole matrix instead. And when you do this, it's just e to lambda 1, e to lambda 2 if you put it to time. So this is very easy to do, and if I write this out fully, then this would equal to x1, x2 dot of time t equals e to our matrix at times x0, which is x1, x2 ... at time 0. Because we solved this at the very beginning, we saw that this was the answer. Good, so we now see why diagonal matrices are so good. So now we want to introduce something. We want to introduce a subspace such that all the eigenvalues and eigenvectors are diagonals. And we saw why this was so good, because if you have eigenvalues and eigenvectors, they follow the characteristic polynomial, which is what we can do. So let's say we have the X subspace. Then we want to take it somehow to this Z subspace, and we want the inverse of this transformation is going to be taking it back to X. So let's say then we're going to call these two transformations, because matrices, they're all about linear transformations, taking it to another way. So it's like perhaps a transformation can be from these coordinates to something like this. And you can watch a 3 blue 1 brown video on it. It's very intuitive, I'd say, matrices and linear transformations. So we'll call this V. So Z to X is V, and X to Z is V to the inverse. And we were talking about how to solve inverses in later videos, actually. Good. Okay, let me just check my notes. And in Z, all eigenvectors and values are diagonal. So the eigenvalues and eigenvectors make up the basis vectors. So this is called the eigenbasis. And by doing so, Z of t equals e to the dt. Oh, sorry, I forgot to introduce something. E to lambda t. And lambda t is going to be the equivalent of the X matrix. So you know how X, we have this A matrix that demystifies, like, that controls the transformation. For Z, it's going to be lambda. So Z, e to lambda t times the initial of Z. So this is why it's so important. It's so much easier to solve. Okay, let me just check my notes one more time. So by doing so, we want... Actually, let me just do a few calculations to help build on intuition. Okay, so let's say we have Z. We apply this V transformation on it. That is going to equal to X. Okay. And that makes sense so far. So we have Z and we apply this V transformation. Then we go back to X. Because matrix C transformations, you go from right to left. So if you take the derivative of both of them, that should equal. And remember, X dot equals AX. So therefore, VZ dot is equal to AX. Okay, that makes sense so far. And then we can get that VZ dot is equal to A VZ. Because we just saw that X equals VZ. Then Z equals inverse of V times A times V times Z. And this is very intuitive for me. This is how I got to understand all of this. We start off in the Z subspace, so we start off with Z. Then we apply this transformation V to take it to X. So we apply this and go to X. Then we apply this transformation A. And if we go back to V negative 1, the inverse, then we get Z. So that makes a lot of sense so far. Then we want V such that V inverse times A times V equals lambda. So if we have V, we do this transformation, then we do this transformation A, then we go back, it should equal to lambda. So V is the one that takes it to Z, which the eigenbasis is the important part. Okay, good. Okay, now what can we do? We can talk about how to construct V and lambda. Let me just quickly erase this. To diagonalize the matrix, we get V. So V, the transformation, and this is going to equal to our eigenvectors. So I'll talk about why this is in later videos maybe. And so they're all in the rows. Now lambda is going to equal to each and individual eigenvalue of t. So since if you take it and you flip it over, then t1 is only going to fit with lambda 1. Then t2 is going to fit with lambda 2. And that makes sense because eigenvalues come in pairs. So that's how we compute that. So good. So now what we can do, I want to go back. We've done with the linear algebra. We're back on this equation. So we're going to take it up here in this space. And what I want to talk about is how, our differential equation down here. What could be the answer for it? Well, a very suitable guess would be that... actually, I don't have enough space. So a suitable guess would be x of t equals e to the at x0. And this is very suitable. But there is something of concern, which is that at is very hard to compute because it's all of these values. It's not diagonal. It's very hard to see. So what I want to do, taking the power of a matrix is very hard. So we have to expand that. E to the at is going to equal to the identity matrix plus at squared over 2 plus at cubed over 3 factorial ... plus ... Now, we all know that the derivative of e to the at is a times e to the at. but let's just see if this is true. So, sorry, not d by dx, it's d by dt. I'm sorry. So, equals, and then the I term goes away. So then we're left with a because t disappears, and then plus a squared t squared, which means that a times 2t. So a squared times 2t over 2, which cancels that out, which means that this is only a squared t. And then plus a cubed t squared over 2. And you will see that all of these terms are just this one multiplied by a. This one was multiplied by a as well. This one was multiplied by a. So it seems that d by dt of e to the at is equal to a times e to the at. And that seems correct because the equation that we're looking at is x dot equals ax. And if e to the at, if we take the derivative, it does seem to be multiplied by a constant again. So this makes a lot of sense. So we are now entering the final parts of our lecture. And we are going to talk about if there are n independent eigenvalues and eigenvectors of the system. So I'm going to erase all of this and then we're going to start talking. Today's lecture one is a really big one, but I'm just really excited about all of this. That is my apologies. Okay, so n independent eigenvectors. So you can always comment whether you like these lecture videos more or these exciting ones. And we recall from just now that A equals V times lambda times V inverse. We remember that, don't we? And e to the at, if we sub in A as this into this Taylor expansion, this one, then we're going to get E80 equals I identity plus V lambda V negative 1 inverse times T plus 1/2 times V lambda squared V negative 1. And I want to show you this one first, really quickly. Why is it V lambda squared V negative 1? Well, because it's here, it says it's supposed to be A squared. So this is t squared first of all, and it says a squared. So how do we compute a squared? Well, that's gonna be v lambda v negative 1 v lambda v inverse. So these two cancel out; they make the identity. So then we erase those two, and we have v lambda squared v negative 1. So I'm so sorry for calling it negative 1. It's really inverse, okay? And we have this. Let's see if I expanded it even more. No, I didn't expand it. Okay, so then a trick that I like is that identity is equal to v and v inverse. So I talked about that just now. So then we can factorize it, and we get that v times the identity, because this is the identity, plus lambda t, because I'm going to take v and v inverse out, plus 1/2 lambda squared t squared, times v inverse, so plus dot dot dot, times v inverse, and this whole thing is equal to, very similar to e to the at, but it's e to lambda t instead. So we can write this as e to lambda t. So therefore we get that e to the at is equal to v e to lambda t times v inverse. So this is so much easier for us because we have a diagonal matrix. So then the solution to any nth order derivative is equal, and this is the best part of the lecture, finding out all this matches, is x of t equals v e lambda t v inverse times x naught, the initial condition. And this is so amazing. All we have to do is transform it into diagonalized matrix, and we can solve any nth order derivative really easily with this diagonalized matrix. So that's all from me today. I hope you enjoyed. Thank you very much, and I hope you learned something.